we discussed in this video about the closure properties of the recognizable languages. So closure properties of rec. And there is really just one main result with several different points that I want to prove. Really what this lemma says is if you have two languages, both recognizable, meaning recognizable by finite automata, whether non-deterministic or deterministic, then you also have the following languages recognizable. You have the union, that's also recognizable language, and you also have the intersection, also the complement of both, and you also have the concatenation of these languages, and also the iteration of these languages. They are also recognizable. So that's the main result I want to prove, and I'm going to prove it in a constructive way, meaning that given such languages, one way or another, you will have a way to really prove the, you will have the ability of building an automaton recognizing all of these languages. So here is the proof. And here is the place where it comes in very handy that we have proved in the previous lectures that non-deterministic automata and deterministic automata are equivalent. So it means that I'm going to be able to switch from one type of automata to the other type without worrying about their computation power. And also I want to comment that really this result is a good tool to build recognizable languages. You will have a few basic languages that maybe you prove directly to be recognizable, and then using these closure properties you will be able to prove quite many other examples to be recognizable as well. So if I prove, so to start the proof, I'm going to say, well, since L is a recognizable language, this means really that the L corresponds to the language of some deterministic finite automaton A, which could be, for example, consisting of states Q and input alphabet sigma, and maybe you have this transition function delta, and some initial state Q0 and some final states. And also L prime was recognizable, so this is also recognized by some deterministic automaton, let's say A prime, consisting of states Q prime. Now, because I do operations on these languages, they have to be over the same input alphabet, otherwise their union doesn't make much sense. So they are over the same input alphabet, some other transition function, obviously some other initial state, and some other final states. And here is an important note. I can assume without loss of generality that really these are different states. Q and Q prime are different states, so their intersection is empty. And if it happens so that they were not, they were not distinct from each other, just rename the states in Q prime, and then you're going to have this condition trivially satisfied. So this is not a big deal, but I'm going to need this condition to be true in my constructions. So here is how the construction is going to go. Again, L is the language of A, with A being Q, sigma, delta, Q0 and F, and L prime is the language of this automaton A prime, with A prime being q prime, sigma, delta prime, q0 prime, and f prime. So if we focus now on the first point, and that was that the union is going to be a recognizable language. And to prove this, I'm just going to build an automaton, and the automaton I'm building, I'm going to just call it A with symbol union here in the index, and this automaton is going to have one new initial state, P0, and this P0 is going to have two epsilon transitions. So this is going to be a non-deterministic automaton. And one epsilon transition is going to be to this state, Q0, and the other epsilon transition is going to be to Q prime 0. And then in here, I'm going to have all the transitions of automaton A. So here is the automaton A with all the transitions specified by transition function delta. And here I'm going to have all the transitions of the automaton A prime specified by the transition function delta prime. And so what this means is that I'm going to have this automaton to be really specified like this. Formally, it's going to have as states all the states of the first automaton, all the states of the second automaton, and also it's going to have this new state. So this is one more state that we didn't have before. So that's going to be the set of states of this automaton, and obviously the same input alphabet as the other ones. And I'm going to have this transition relation that I specified here. Then the initial state is going to be this P0 in here. And for final state, I'm going to choose whichever final state, so all the final states of the first automaton and all the final states of the second automaton. And so when we think about the computations going in this automaton, you've got to realize that you're going to start the computations in P0, and then the very first move you do will be an epsilon transition, which essentially is going to choose between the first automaton or the second automaton. And once you made your choice, then the computation goes as it went in this automaton, or if you made this choice, the computation is going to go according to this automaton, and it's going to read letter by letter from the input until eventually at the end of the input it's going to reach a state, and that state is going to be final or not according to this automaton. But because of the way we have defined the final states, if it was final in the automaton A prime, it would be final in the big automaton. So in other words, what I'm saying is this automaton is going to accept any word that's accepted in this automaton and any word that's accepted in this automaton. So with this simple argument, we can see that the language of this automaton is exactly the language of A. All the words accepted by A are also accepted by this one, and language accepted by A prime. So that's exactly L union L prime, which is what we wanted. So indeed, the union is a recognizable language. For the complement, so if I take the complement, I need to prove that this one is a recognizable language. This is a very easy construction. I'm going to just build this automaton, which essentially is going to go exactly like A, with just one exception. I'm going to use the same states and obviously the same input alphabet, and even the same transition function, and even the same initial state. But here I'm going to use as a set of final states exactly Q minus F. So in other words, this automaton is going to accept whenever this automaton was rejecting, and is going to reject whenever this one is going to accept. So it's really easy to see that the language of this automaton is exactly sigma star minus the language of A, which is really the complement of language L. Now, to see about the intersection, to see that this is indeed a recognizable language, you could also just, simplify your life and make the following argument. Well, it's got to be recognizable just based on these 2 points we have proved before, because really by applying the De Morgan rules, this is the same as having the complement of L and L prime union and applying complement at the end. And all of these things, the complement and the union, and again applying the complement, all of these things we have shown that preserve the recognizable character of these languages. So you could do this. But as a matter of fact, I think that it's really educational to think about a direct construction. And the direct construction goes something like this. So what I would like to do here is really this kind of how should I say, sort of a Cartesian product of the two automata. So this is automaton A, and this is the automaton A prime. And this one starts computations in Q0, and this one starts in Q prime 0. And somehow I would like to suggest that we do a Cartesian product, meaning that we are going to start our computation in this initial state, which is the Cartesian product of Q0 and Q prime 0. And if this one was going to this state, whatever it was in here, and this one was going into this state, then the new automaton is going to go into the pair of these two states. So with this simple trick of thinking about the Cartesian product, what we do essentially is we run in parallel two simultaneous computations on the input word, one on automaton A and the other one on automaton A prime. And we are going to accept if both of these computations end up in some states that this one belongs to F and this one belongs to F prime. So only then we will accept the input word. So I think this requires a little bit more explanations, and I'm going to give it. So what I do is for this automaton, for this point, I'm building this automaton A intersection, and this one is going to have as the set of states exactly what I said. It's Q times Q prime, so the Cartesian product of Q and Q prime. And the input alphabet, obviously, sigma, and I'm going to build a new transition function. Let's say maybe I say delta intersect. And as the initial state for this automaton is going to be the pair of Q0 and Q0 prime. So as I said, we start in the initial states of the two automata. And as the final states, I'm going to take F times F prime. So I really have to end in a pair of states, one final in the first automaton and the other one final in the second automaton. So the only thing that requires explanations is this, how do you define this delta intersect? And really delta intersect of applied to a state. So a state maybe something like P and P prime with letter A is going to be a pair. And on the first component, you are going to have delta of P and A. So you do the computation in the first automaton with delta. You apply on state P, you apply transition A with delta. And on the second component, you do the same computation in automaton A prime. So this is going to be delta prime applied to this state, P prime with letter A. So that's going to give you the two parallel computations you need. And really, it's now easy to see just based on this argument that you do two computations in parallel, and you've got to end in a final state both in the first automaton and in the second automaton. It's easy to use this argument to conclude that the language of this automaton that I just built is exactly the language of the first automaton intersected with the language of A prime. And again, the point is, I'm going to accept only those input words that reach a final state on the first component, meaning in this automaton, and they reach a final state on the second component, meaning on this automaton. So hence you have this intersection. And so obviously this is L intersected with L prime. Now for the concatenation, so if I am to prove that L1 times L2, it's a recognizable language, the automaton I'm going to build is simply this one. I'm going to just take automaton A, and this one starts from Q0, and my new automaton also is going to start from Q0. So this is going to be the initial state. And for any final state, maybe you have several of them. So you are going to have an epsilon transition to the initial state of the second automaton. So for all of these final states, you will have an epsilon transition here. And you are going to end up with whatever final states you had in here, and they are also going to be final states for the automaton I'm just building. So this automaton is going to go like this. It starts in Q0, which is the initial state of the first automaton, and for a while it does a computation in automaton A until it reaches a final state in the first automaton, meaning that in the prefix of your input word, there has got to be a word accepted by automaton A. And then you have an epsilon transition, and the second automaton has to read and accept the second part of your input word. So with this argument, it's easy to see that the language of this automaton is really made of words of this type, U concatenated with V, U being in the language of A, and V being in the language of A prime. And that's exactly the definition of the language of A concatenated with the language of A prime, which is exactly L times L prime, which is what we wanted to prove. And so finally, for the iteration, so if I want to prove that L star is a recognizable language, I'm just going to build this automaton A star, and this is going to take the automaton A, and remember this was starting in Q0, and it was ending in a bunch of final states, and the only thing it does is going to add an epsilon transition from any final state to the initial state Q0, and also is going to make Q0 a final state itself. So what this does intuitively, first of all, by making Q0 a final state, I'm going to add the empty word in my language. And then for all the other words that I want to accept, what I have to do is I have got to run a computation in A and reach a final state. And either I stop there, or in fact the input word is longer, and then with an epsilon transition I move back here, and again I have to do another successful computation until I reach a final state. And then either I stop or I have one more iteration in my automaton A. So with this argument, it's certainly clear, at least intuitively, and a more formal proof can also be given, but I'm going to skip it here. It's easy to see that it's really the iteration of the language of A, and this is obviously L star. And so with these constructions, what we have now is that we can prove a number of examples just based on languages that we've seen in previous lectures. And for example, I could just list here a few such things. Remember that we had in one of the previous lectures, for example, the language L, consisting of words over alphabet A, B, in such a way that W has ABA as a factor. And just to convince you one more time that this is indeed so this is a recognizable language, and just to convince you of this, it's really easy to see this. For example, you just have this automaton. It stays in state 0 with A and B, and then with A it goes also here, and with B here, and with A it goes into this state, and this is an initial state, and that's a final state. And then in this state it can also stay as long as you want. So that's an easy way of seeing that this language is recognizable. But just based on this, we also have, for example, that as a consequence, for example, all the words in AB star, the property that ABA is not a factor of W. So this language is obviously the complement of L. So that's also a recognizable language. So not having a factor, that's a recognizable language. But here is another one. If I say, I just want all the words in AB star in such a way that ABA occurs twice, or occurs twice as a factor in W with non-overlapping occurrences. And this is also recognizable because you can see right away that this is really L concatenated with L, and that makes it a recognizable language. Or you can also, for example, prove that if you take all these words, A, B star, such that, you can say either ABA or BBB is a factor of W. This is the union of two very similar languages, one of them being the one with ABA as a factor, so the one that we had before, and this one being, in a very similar way, the set of words with BBB as a factor. And very similarly, we can see that L prime is a recognizable language, and so that union is a recognizable language as well.